Okay, so here in this class, we'll take up next problem on bending stresses over here. So this is the problem: a T-beam with a flange of 100 mm by 20 mm and with a web of 20 mm by 100 mm is used as a simply supported beam over a span of 8 meters. It carries a uniformly distributed load of 1.5 kilonewton per meter throughout the length. Determine the maximum compressive and maximum tensile stresses and plot the variation across the depth of the beam. Okay, so here is the beam what we have: 8 meter span, and the UDL what it is carrying is 1.5 kilonewton per meter for its entire span. Now in cross section, you'll find that it is a T section. The dimensions are given to us. So this flange width, it is 100 mm. These are all in mm, and the thickness of the flange is 20 mm. For the web, the depth of the web is 100 mm, and the thickness of web is 20 mm here. Okay, so we need to find the maximum tensile and compressive stresses here. Okay, and these are the bending stresses. So for that purpose, first is we need to know what is the maximum bending moment in the beam. For a simply supported beam supporting UDL for its entire length, the maximum bending moment will occur at the mid-span, and it will be WL square by 8. So here maximum bending moment maximum bending moment in the beam will be at the mid-span. We need to mention the location where that maximum bending moment will be. At that point itself, we'll get the maximum stresses in the beam. So this is the location, and this maximum bending moment, let us take that to be m. It will be equal to WL square by 8. Okay, and the beam is subjected to sagging moment. This is sagging moment, right? So what it comes out for us, m will be W is 1.5 kilonewton per meter, L is 8 meters, WL square divided by 8. So we have m equal to, it will be 12 kilonewton meter. That is 1.5 into 8 square by 8. So this comes out to be 12 kilonewton meter, or you can also take it as 12 into 10 raised to 6 Newton mm in terms of Newton mm. Now the next thing is we need to locate where is the neutral axis for this beam. Okay, so in case of this straight beam, what we have is the neutral axis will coincide with the centroidal axis over here. So we'll have to locate the centroidal axis to know the position of neutral axis. So we'll do it by taking the moment of areas about this reference axis, which we have considered as neutral axis at present. So let us say this is our neutral axis position over here. So we have two areas in our section, the flange and the web. Both are rectangular in cross section, and here I'll call this as the neutral axis. Okay, and let us say the distance is y bar from the top of the flange. Okay, so now position of neutral axis. Neutral axis. Okay, for that I'll just take this expression which we use for the location of centroidal axis: a1 y1 bar plus a2 y2 bar divided by a1 plus a2. Okay, So this will be A1 100 by 20. That is what we have. Okay, this is the cross section which we are having here. So fine. So what it comes out, y bar will be A1 flange area into 20. Okay, this is our A1 and A2. Okay, so centroidal distance of the flange from the top, it will be 20 by 2. Y1 bar will be 20 by 2 here, plus A2 is this rectangular section which is there for the web, which is of 20 by 100. Width is 20, depth is 100 mm. So A2 is 20 by 100. And where is the centroid of this from measured from the top of this flange? It will be 20 plus 100 by 2. So 20 plus 100 upon 2, t by 2 is the location of centroid for a rectangle section, and divided by A1 100 into 20 plus A2 20 into 100. Okay, so what will be this y bar equal to then? We have 100 into 20 into 20 by 2 plus 20 into 100 into 20 plus 100 by 2, and whole thing divided by A1 100 into 20 plus A2, that is 20 into 100. So y bar, it comes out to be 40 mm. Okay, now we have the location of neutral axis here. Okay, this is 40 mm from the measured from the top of the flange here. What we require next is what is the moment of inertia of the section. Moment of inertia of the T section about its centroidal axis or about the neutral axis. Okay, so this can be obtained by applying the parallel axis theorem, which is I equal to IgG plus A into YC square here. So we have two areas. For both the areas, we will apply the parallel axis theorem. When I take the A1 area, flange area, so there IgG comes out to be B 100 into D cube 20 cube by 12 BD cube by 12 plus A 100 into 20 into what is the YC value here? It is the distance between the centroidal axis and the CG of the individual area here. Okay, so if I deduct this 20 by 2 in my y bar, I'll be getting YC for the first area. So that will be 40 minus 20 by 2 square of this. Okay, this is the YC for the A1. A1, the centroid is at a distance of 20 by 2 from top of the flange. Okay, so if I find the difference between y bar and this 20 by 2, that itself will be the YC term. Okay, distance between the axis about which you are determining the moment of inertia and the centroid of the area. Now for the second one, what we have, it is B20 into D cube by 12, that is 100 BD cube by 12. This is the moment of inertia about its own centroidal axis, plus area 20 into 100 into YC. What is the YC term now? So here YC is this 100 by 2 plus 20 minus Y bar. Okay, so that will be 100 by 2 plus this thickness of the top flange 20. Okay, this I'll be deducting in Y bar. Okay, or the value of Y bar is 40 mm. What we have here, 40 the whole square. So this will tell me what is IGG or I value for the entire T section. So what it comes out here now, if you calculate this, we'll be getting this I value for the entire section as 5333.33 into 10 to the power 3 mm raised to 4. Okay, so that is our I value, moment of inertia of the T section about the neutral axis. Now bending stress, or actually we are finding the maximum bending stress. So maximum bending stress. First, what you are asked is to determine maximum compressive and maximum tensile bending stress. So since the beam is under sagging condition, the top fibers, the fibers in this towards this top flange will be under compression, whereas the fibers towards the bottom of this web will be under tension. So we'll be taking the distance up to the top of the flange and the bottom of the web to determine what are the maximum compressive and tensile stresses. So first case, when I try to determine maximum stresses, bending stresses in tension, okay, or in compression, let us do that first. In compression, okay, so what I'll be doing is I'll be considering this flexural formula, m by I is equal to sigma by y here. Okay, now for this case y, or I'll be taking y top. Okay, the distance of fibers towards the top of the section, y top, it will be nothing but it will be equal to y bar itself. So this is 40 mm. This is the maximum distance towards the top of the section. So we have what is the value of m now. We have already determined what is the maximum bending moment. So that will be the value what we'll be using in this expression. And also we have determined the moment of inertia I value for the section. So from that, what I have, moment bending moment, maximum bending moment is 12 into 10 raised to 6 here. Okay, so first is we require this stress value, bending stress, so that can be expressed as m by I into y. Okay, so this will be 12 into 10 raised to 6 divided by I value 533.33 into 10 to the power 3, okay, into, just a second, into, I'll be multiplying y top, because I'm calculating what, first the maximum compressive stress here. Okay, So into that is 40 mm, right? So this will tell us what is sigma or the maximum compressive stress, maximum bending stress, compressive stress in the beam. So 12 into 10 raised to 6 divided by 533.33 into 10 to the power 3 into y top, that is 40 mm. So we are getting this as 90.0 Newton per mm square. Okay, so this is compressive. Okay, that is a compressive stress, maximum compressive stress. Next, in tension, I need to know what is a maximum bending stress in tension. Same, I'll be applying the flexural equation for the bending stress, m by I into y. But in this case, bending stresses, maximum tensile bending stress will occur at the bottom. So we'll consider the extreme fiber distance towards the bottom. How much that comes out here? So this overall depth is 120. If I deduct y bar in this overall depth, I'll be getting the distance for the towards the bottom of the section, maximum distance of the fiber towards the bottom of the section. So what this will be? This will be 120 minus 40, that is 80 mm. Okay, because y bar was 40. Okay, overall depth it is 120. So in this 120, if I deduct y bar, this distance, so that is 40 mm. So this will come out to be 80 mm. So extreme fiber distance towards the bottom is 80 mm. Now if I substitute the values of bending moment, which is 12 into 10 raised to 6, and the moment of inertia, that is 5333.33 into this into 10 raised to 3, and y bottom it is 80 mm. Okay, so that will give me what is the maximum tensile bending stress. 12 into e raised to 6 divided by 5333.33 e raised to 3 or 10 raised to 3 into 80. So maximum tensile stresses, they are coming out to be 180.0 Newton per mm square. These are tensile. Okay, so that is the stresses what we have in that section. Now to plot this, okay, and plot the variation across the depth of the section, it is asked to plot the variation of the stresses across the depth of the section over here. So that we'll do it over here. So once we know maximum variable stresses, what we have, okay, so this is the section. This line represents the depth of the section here now. Okay, and on the top, what we have is the compressive stresses. You can choose any one side as compressive stress. So maximum compressive stress was 90 Newton per mm square. So that is, this line is representing, this arrow is representing the compressive stress. Okay, I've taken compressive stress towards the right. That is the direction what I have chosen there. Now on the bottom, what we have is tensile stresses. So the direction should be opposite to that, what we have chosen for the top one. So this is the maximum stress at the bottom, which are tensile in nature. So the variation here will be linear. As you vary the y distance of extreme fiber from the neutral axis, that will tell you the variation. So y is varying linearly, and our stresses within the across the depth of the section will also vary linearly over here. So this is what I have, this compressive stress as 90 Newton per mm square, and tensile stress as 180 Newton per mm square. Okay, so within the section we'll come across this variation. So towards the neutral axis, the compressive stresses will start reducing. At the neutral axis, the stresses will be zero, and when you come below the neutral axis, the tensile stresses will be there, and they will increase as you move towards the bottom. Okay, you can choose the sign convention. You may take that tensile stresses to be positive and compressive to be negative, or vice versa. So this is the variation of the stresses across the depth of the section. At the neutral axis, they will remain zero. That is the point you need to note. And the extreme fibers, top and bottom fibers, they will be maximum. When beam is under sagging condition, towards the top fiber, maximum compressive stresses will occur. Towards the bottom fiber, maximum tensile stresses will occur. Okay, the next one, this is what we have here. So what is asked is, a horizontal beam of the section shown in the figure is 4 meter long and is simply supported at the ends. Find the maximum uniformly distributed load it can carry if the compressive and tensile stresses are not to exceed 60 MPa and 30 MPa respectively. Okay, so in this case, we have the stresses given to us. What are the permissible stresses that are allowed in the cross section of the beam are told to us, and we need to find what UDL it can carry. Okay, so maximum uniformly distributed load that the beam can carry has to be determined here. So for that purpose, uh, we'll work with the flexural formula only. So for the given cross section, the first thing is we need to determine the location of neutral axis and also the moment of inertia here. So here what I have, this section, so this is our section, what is given here. These are all the problems from the video question paper, previous video question papers, all these three problems. So the thickness is 20 mm, and these two areas, they are of 100 mm depth. We'll mark the areas over here. So let us say we'll call this as A1, A2 and A3. These are three areas, and we'll take our neutral axis to be somewhere at this position. Let us assume that the neutral axis is at this position, what is shown here. So that is the position of my neutral axis, what I have assumed. We need to determine what is the distance of this neutral axis. We'll consider the bottom of the section as a reference. With respect to that, we'll determine what is the position of our neutral axis here. So for that, we'll take up that position of neutral axis. Okay, so with respect to this bottom of the section, let us say it is y bar. Okay, position of neutral axis means you need to determine the position of the centroid of the section. So y bar in this case will be a1 y1 bar plus a2 y2 bar plus a3 y3 bar divided by, so this position neutral axis this whole thing divided by A1 plus A2 plus A3. We have three areas. So what I have A1, okay. So A1 is 120 by 20, 120 into 20 mm, okay. Y1 bar from here it is 20 by 2 from the bottom of that section, 20 by 2 here, plus 2 into, because the other two areas are same, they are of 80 by 20. Already we have taken this bottom 20 mm thickness over here, so I'll just multiply 2 into A2 and A3 are same, so this is 80, okay, width is 20 mm, so B into D, so 20 into 80 into, what about the centroid? It is somewhere here, 80 by 2 at a distance of 80 by 2 plus this 20 mm. So it will be 20 plus 80 by 2 over here. This is A1 plus A2, A1 Y1 bar plus A2 Y2 bar plus A3 Y3 bar. Whole thing divided by 100 by 20 plus 2 into 20 by 80. Okay, so this will give us what is that Y bar. So if you calculate that, 120 into 20 into 20 by 2, that is Y1 bar, plus 2 into what, 20 into 80 into 20 plus 80 by 2, and whole thing divided by the total area, which is 100 into 20 plus this twice 20 into 80. So we are getting it as 41.54 mm. This is 41.54 mm over here. Okay, that is the Y bar value. Now after we have done that, next is moment of inertia of the section. So again go for applying the parallel axis theorem to determine the moment of inertia over the neutral axis or the central axis. Both are same in our case. So here moment of inertia of the section of that channel section, actually it is a channel section here, what is shown to us. Okay, so for this section, what is the moment of inertia, that will determine over here. We'll take this one. This is the section, we'll keep it here, and then what we have, so I, this is the expression what I'll be using here. The moment of inertia of the entire channel section will be equal to IgG plus A into YC square. Okay, moment of inertia about its own central axis plus A into YC square. YC is the distance between the centroid and the axis about which you are calculating the moment of inertia for the section. So here what we have, if I take this first one, A1, okay, that is BD cube by 12. Since all are rectangle sections, this moment of inertia about the centroid IgG will be BD cube by 12 for individual areas. All of them are rectangles, so this will be applicable for all. So here B 120 for first bottom area into D20 cube divided by 12 plus 120 into 20 into y square. So with respect to this bottom, it is over here. The centroid is at a distance of d by 2 measured from this edge. So it will be directly 20 by 2 square. Okay, plus what I have, another two areas are. So 2 into, what we'll do is directly 2 into, what is width? 20 mm. Okay, 20 into 80 cube. The depth of those two webs, or these two lips of the channels, will come out to be 80. That is this 100, this was 100. Okay, 100 minus this 20 divided by 12, BD cube by 12, plus A 20 into 80, okay, into YC square. What is this YC now? This is the CG of this individual areas. Okay, what is the distance? 80 by 2, D by 2 from the either end. Okay, D is 80. So measure from the bottom, what will be this distance? 20 plus this D by 2. Okay, so that will be 20 plus 80 by 2 here, square of this. Okay, so this will give us what is the I value for the entire channel section about the neutral axis. So how much it comes out here now in this case? So the value is coming about 13,546, 13,546.67 into 10 to the power 3 mm raised to 4. Okay, this is the value of moment of inertia, what we have obtained here. Now, once we have the moment of inertia and the location of the centroid, now we'll go for applying the equation of flexure or bending equation, the flexural formula. So what it says, now first if I consider this flexure formula, it is this m by I is equal to sigma by y. Actually, if you look into the full formula, it is having three ratios. M by I is equal to E by R, and that is equal to sigma by y. Okay, but what I am considering for our problem, it is the first and this last two ratios. Okay, from this I can obtain what is the moment of resistance of this section. So M comes out to be sigma by y into I. Okay, now what we have is, we are given with this value of sigma. What is told to us? The permissible stress, okay, in compression is 60 and in tension is 30. So we have this value of sigma. So for permissible compressive stress in, or permissible compressive stress is 60, and sigma value is 30 Newton per mm square or MPa under tension. Okay, so these are the two values. Now what about y here? Okay, so y bar we determined, we have the value of y bar here. Now it is known to us, it is 41.54 from the bottom. This value, what we determined, it is this y bar. This is the y bar value. So when the beam, okay, it is simply supported and it is carrying a UDL, so it will be under sagging condition. When it is a downward load which is acting on the beam, okay, so we'll assume this to be a downward load only. Normally the beams are subjected to gravity loads which will be acting in a vertically downward direction. So under such a condition, beam will be subjected to sagging movement. Okay, so here bottom fibers will be under tension, top fibers will be under compression. Now we'll go for determining the moment of resistance for considering both of the permissible stresses here. So if I first consider the moment of resistance by taking into the permissible stress and tension. Okay, so moment of resistance of the section. So first is sigma 30 Newton per mm square tension, permissible stresses under tensile are 30 Newton per mm square. So this is what you have. And where these tensile stresses are coming out, they are at the bottom. So y bottom. What is y bottom? It is nothing but our y bar itself. Distance of extreme bottom fiber measured from neutral axis, it will be equal to this y bar 41.54. So here y bottom, it will be 41.54 mm. Okay. Under this condition, what will be the moment of resistance of the section? M, which is MR. In this case, we'll call it as MR over here. Moment of resistance, that comes out to be 30 Newton per mm square divided by 41.54 into I. What was the I value we had? 13,546.67 into 10 raised to 3. So this will be into 13,546.67 into 10 raised to 3 over here. So this is what we have, the moment of resistance of the section. And this is equal to 9.78 into 10 raised to 6 Newton mm, or it can also be expressed as 9.78 kilonewton meter here. Okay, so this is by considering the maximum permissible stress under tension. Okay, the same when we consider the maximum permissible stress in compression. By considering the maximum permissible stress in compression, if I determine what will be the moment of resistance of the section, so we'll get to know what will be the least moment carrying capacity of the section from both of these values. So in second case, what I'll do is I'll take sigma equal to 60 Newton per mm square. So top fibers are put in compression. Top fibers are subjected to compression, and this y will be now y top, which will be equal to this overall depth of the section minus y bar. Overall depth of the section is 100 mm. So 100 minus 41.54. Y top will come out as this 100 overall depth of the section minus 41.54. So that will be 100 minus 41.54. So that is 58.46 mm. 58.46 mm will be our y value or y top. Now again, moment of resistance we will be determining by taking the Flange formula only, that is sigma by y into I. So what you have, sigma is 60 now divided by 58.46 into 13,546.67 into 10 raised to 3. So what that comes out, let us see, 60 divided by 58.46 into 13,546.67 into 10 raised to 3. So in this case, we have the value as 13.903. 13.903 into 10 raised to 6 Newton mm, or we can also write it as 13.903 kilonewton meter. Okay, now we have two moment of resistance, one 9.78, other 13.903. Out of these two, this is the least one. Okay, so the beam can at the maximum support 9.78 kilonewton moment. Therefore, we have maximum bending moment in the beam as 9.78. This is the maximum bending moment that the beam can take. Okay, so maximum bending moment the beam can withstand. Okay, that is 9.78. Now for a simply supported beam, what we have, the maximum bending moment, what will be coming in the simply supported beam, that will be WL square by 8 at the midspan, WL square by 8. Now what I'll do is I'll equate this value to WL square by 8. Therefore, 9.78 will be equal to W into, for our beam, span is 4 meters, 4 square divided by 8. Or the intensity of the UDL that the beam will support will be 9.78 into 8 divided by 4 square. It is 4.89 kilonewton per meter. So W will be 4.89 kilonewton per meter. That is the maximum uniformly distributed load that the beam can carry. Okay, for this particular section, what is given to us, right? So this is what you have. This is how we arrive at the maximum load which beam can support in case when we are given the section and the permissible stresses in tension and compression. Okay, next one, what we have here. So this is one more problem from previous question papers. So this is what is the problem which is given here. A circular pipe of internal diameter 70 mm and thickness 8 mm is used as a simply supported beam over an effective span of 2.5 meter. Find the maximum concentrated load that can be applied at the center of the span if permissible stress in the tube is 150 Newton per mm square. Okay, so in this case, the cross section what we have is a hollow circular cross section. So this is the cross section what we have in our case. Okay, so that is our cross section, and the diameter, internal diameter is 70 mm. That is this internal diameter, it is 70 mm here, and also the thickness of the section is given to us. So this is 70 mm. And what about the thickness? The thickness of this wall, it is 8 mm. So this wall thickness is 8 mm. Okay. Now neutral axis. In this, the position of neutral axis you can determine straightforward. That is, the neutral axis will be exactly passing through the center of this circle. Okay. So that is the position of neutral axis. It will be symmetric, and for a circular section, the centroidal axis will be coinciding with the center of the circle here. Okay, so this is the neutral axis what we have. And what about the moment of inertia of the section? So for a circular section, the moment of inertia will be pi d raised to 4 upon 64. Since it is a hollow circular section, this inner portion of the area has been removed. Okay, so let us find out these two. neutral axis, first is neutral axis passes through the center of the section. This happens in case of a circular sections. And I value moment of inertia about this neutral axis. Okay, so that will be pi d raised to 4 by 64. Okay, but in this case we have a hollow circular section, so we'll be deducting this moment of inertia of this inner circle, okay, from the outer circle. So what you have, outer diameter is 78 mm here. Sorry, in outer diameter how much it comes out, 70 plus 8 plus 8, so that will be 86 mm. Outer diameter will come out to be 86 mm. Inner diameter plus 2 thicknesses. Okay, so this will be the outer diameter what we have measured from here to here. Okay, so this is 86 mm here. Okay, that is outer diameter, whereas inner diameter is 70 mm. So to get the moment of inertia of this entire section, I'll simply take pi into 86 raised to 4, pi d raised to 4 by 64 minus pi into 70 raised to 4 divided by 64. Moment of inertia of the outer circle minus moment of inertia of the inner circle, which has been removed from that section. So that will be is somewhere around 1506.53 into 10 raised to 3 mm raised to 4. Okay, and what we have next is to find out what is the moment of resistance first. Then we'll go for determining what load the beam can support here. So moment of resistance we can obtain by considering the flexural formula over here. So what we have here is the flexural formula. So if I write that flexural formula, so we have it as m by I is equal to sigma by y. Don't forget the complete equation what we have is m by I is equal to E by R is equal to sigma by y. In that we are using first and third equations, and moment of resistance can be expressed as sigma by y into I. Okay, now for our section what we have here, y top, okay, and y bottom will be same, and they will be equal to half the diameter of the external diameter here, that is d outer diameter by 2. So that is 86 upon 2, which is equal to 43 mm. 43 mm here. Okay, now what about the moment of inertia? Sorry, the moment of resistance. So what we are given, the permissible stress in the tube is 150 Newton per mm square. Nothing has been told that whether it is in tension or compression, or we can take it as the permissible stress in tension and compression both are same, which are equal to 150 Newton per mm square. Okay. So in this case, when permissible stress is 150 Newton per mm square, so sigma is 150 Newton per mm square. Okay, therefore M or moment of resistance will come out to be 150, okay, divided by, this is 43 into 1506.53 into 10 raised to 3. Okay, so how much will be the moment of resistance in this case? That comes out to be 5.255. 5.255 into 10 raised to 6 Newton mm, or 5.255 kilonewton meter. Okay, so in case a simply supported beam is carrying a concentrated load at the center, okay, so we have maximum bending moment as WL by 4. So in that case, I'll equate the moment of resistance to that maximum bending moment. So maximum bending moment for a simply supported beam carrying concentrated load at midspan will be equal to WL by 4. Therefore, what we have, we will equate this moment of resistance 5.255. So 5.255 kilonewton meter will equate it to the maximum bending moment. L is how much? 2.5 meters. So W into L 2.5 divided by 4, or the magnitude of concentrated load, it will be 5.255 into 4 divided by 2.5. It is 8.408 kilonewtons. That is the maximum concentrated load the beam can support at the midspan. Okay, so this is how you find the load that the beam can support, maximum load the beam can support. Okay, these were the three problems what we have taken up from our previous examination question first.